So this is what we did in last class. We had arrived at an equation for hydrogen atom, Schrodinger equation for hydrogen atom, and then we changed the coordinates into r, theta, and phi, and we could separate it into uh, so. Okay, so there is some problem with my slide changer, otherwise it should have worked. ठीक है, इसको replace. So क्या गिरीश सर वाला भी नहीं है अभी उनके पास है. ये वाला, ये तो पूरा कीबोर्ड है इसमें. बैटरी तो हम लाए हैं. ओके ओके ओके, पॉइंटर तो मेरा भी काम कर रहा है. स्लाइड चेंज होगा इससे? स्लाइड चेंज इससे स्लाइड चेंज होगा? गोइंग टू going to learn about is the radial wave function, radial part of the wave function. So radial wave function was so this is radial part of the wave function and angular part of the wave function, which is given by Legendre. आइए, completed your experiment. So it is your responsibility whether you complete 1, 2, 3 or 4, जितना कर सकते. 3 किया. हाँ ठीक है. So radial equation was given this kind of. So when you are replacing u with r, both were interchangeable. Earlier to simplify mathematics we had defined u, and now we are replacing that again. फिर से वापस कैपिटल आर के टर्म्स में सारी इक्वेशन को लिख रहे हैं. ठीक है. सो इनिशियली हमने ये डिस्कस किया था कि that the effective potential energy has two terms. One is the electrostatic, other one is the centrifugal effect. ठीक है. So when L is 0, there is no centrifugal effect. You do not have any momentum due to the orbital motion in that case. So we further analyze this radial part of the wave function, and Coulombic potential, that was centrifugal effect, and originates from the classical physics that you can think of anything rotating around a central object will have centrifugal force acting on it. So that kind of thing. Only in case of L is equal to 0, there is no angular momentum. Okay. So that was the point that many of us were considering, that इसमें क्या होगा. So वहीं पे मैंने आपको कहा था कि yes, there will be, in that case you have maximum electron density at the nucleus. So that is really true. That happens for s orbitals. For all L is equal to 0, non-zero values of L, there is a positive centrifugal contribution which is repulsive in nature and takes the particle away from the nucleus. So that kind of so there is attractive Coulombic potential, Coulombic term. This is attractive in nature. Centrifugal, this is repulsive. It will take away the particle, the electron, from the nucleus. So initially what I told you, that it is the centrifugal term dominates It is more dominant as compared to the Coulombic term, which is proportional to 1 by r. So very close to the nucleus, you have the graphs were something like this. Sorry, here. So uh, so qualitatively, we analyze that particular thing very close to the nucleus, how it behaves, and that was something that we learned last time in the last class. For L non-zero value of L, potential sharply rises beyond 0, becomes positive and rises like this. For L is equal to 0, it goes on decreasing continuously as it approaches the nucleus. Okay. So this was the effective potential energy of electron in the hydrogen atom. So this is the way we describe the. So what you saw here, a well type of thing was being formed for anything non-zero L. So somewhere in the middle, somewhere very close to the nucleus at this point, you have minimum potential energy. But in this particular case, there is no such point appearing. Minimum potential energy wala well jaisa point. So there is no well-like curve appearing in this. Instead, you have a constantly decreasing profile. So centrifugal effect uh, is it is giving a positive contribution, as you can see here, and it is very large. Suddenly it rises very sharply beyond 0, so it becomes positive and rises very sharply very close to the nucleus. So because of this reason, we expect that when L is equal to 0 or L is not equal to 0, in these two cases the wave functions are also going to be very different. वेव फंक्शन का जो नेचर होगा, प्रोफाइल होगा, वो भी काफ़ी अलग होगा एक दूसरे से इन दीज टू केसेस. सो एस ऑर्बिटल के केस है जहाँ पे L इक्वल टू 0 है, that indeed has a very different profile from all other wave functions. We will see that later, very soon. Okay. थोड़ा सा टिल्टेड नहीं लग रहा है, स्क्रीन थोड़ा सा अधूरा लग रहा है. So what we do here, we have two terms. We will keep we can ignore the largest term. So what we have done here, when, as we said, very close to the nucleus, it is the centrifugal term that dominates, and in comparison to that, this particular can be neglected for distances very close to the nucleus. And so we can rewrite this same equation, can be rewritten यहाँ से यहाँ. ये V इफेक्टिव में जो दो टर्म था, सिर्फ एक को हमने रिटेन किया और approximately equal to, or you can write. So this was the basic idea, and from here we started thinking of what kind of equation can fit in this double second differential equation of second order. So in general, in mathematics, this kind of formula fits this equation, differential equation. It can be found, it can be treated as a solution to this kind of equation. Okay, so to verify that, this is the way we have been doing all along. If you think something is can satisfy that differential equation, it is a solution to that differential equation, then you substitute it and then you prove it that it is actually doing it. There is no direct solution that you can get. You can only hit and trial. You can define certain equation and try to put it in that equation and then find out whether it's satisfying all these things. So substitute it and verify. So you can have R, the capital R is the wave function that I told you, the amplitude of the wave, how it varies with respect to the radial distance. So because R cannot be infinite, so here when you place R is 0, R to the power L somehow, if this term goes to 0, then this term becomes infinite. So to get rid of that, we set b is equal to 0. So this is gone, and we are left with r to the is equal to a to the power rl. So this is the simplification, and we can write then the equation can be then written as this. So d second derivative of u, that is r u is this r into small r into capital R, can be written, and finally you can write this as r d2r by dr square. So this is the equation. So this equation we have transformed into a very simplified, relatively simpler equation in terms of mu and small r, that is the radial distance, the variation of. So the thing acceptable. So finally, the acceptable solution will have look like this: exponential with r term appearing. So it is a exponentially decaying function. मतलब exponentially decrease आपको दिखे. So exponential decrease of the amplitude will be there as per this function. And then we looked at this specific term r to the power L. Closer to the nucleus, wave function is proportional to r to the power L. Far from the nucleus, you can expect it is decay exponentially to 0. So squaring this gives you electron density, and electron density, then you multiply. So this particular thing, electron density, is also, you can call it probability of finding electron at a specific point. Okay, and sometimes it is also described as probability density. So the terminology which you may come across in different books, all of them has been summarized here: electron density, radial density, probability of finding electron at a specific point, or probability density. All are same thing. But so radial wave function profile very close to the nucleus. So now we are looking at, after understanding the profile of how the potential energy varies when L is 0 and non-zero, we have perfectly guessed the kind of wave function that we have that can satisfy these equations, satisfy the differential equation. And so the very close to the nucleus, this is how it behaves. When L is 0, you have a maximum amplitude of the wave appearing over here. Okay? So this profile is very, very different from all other values, all other wave functions when L is non-zero, like 1, 2, 3. You can see at the nucleus it is always 0. मतलब s ऑर्बिटल को छोड़कर बाकी सब में एम्पलीट्यूड 0 है. जो इलेक्ट्रॉन एज अ वेव हम ट्रीट कर रहे हैं, उस इलेक्ट्रॉन वेव का एम्पलीट्यूड 0 है यहाँ पे न्यूक्लियस पे. लेकिन s ऑर्बिटल में जो इलेक्ट्रॉन वेव है, that has maximum amplitude at the nucleus, and square of that gives you electron density, radial electron density. So electron density is maximum for s orbitals at the nucleus. At the nucleus it is maximum. ठीक है. और बाकी जैसे जैसे 1, 2, 3 सेंट्रीफ्यूगल इफेक्ट यू कैन सी. सो अब आप थोड़ा और ध्यान से देखेंगे. 1 इज राइजिंग लाइक अ स्ट्रेट लाइन. 2 थोड़ा सा और पीछे हट गया, मतलब धीरे धीरे राइज कर रहा है. इट इज रिमेनिंग 0 फॉर क्वाइट सम टाइम. यहाँ पे देखिए, ये यहाँ पे 0 था लेकिन फिर उठना शुरू हो गया तुरंत. बट उसके ये थोड़ी दूर तक 0 0 जा रहा है, ऑलमोस्ट टचिंग द 0 लाइन, एंड देन राइजेस बिकम्स नॉन जीरो हियर. देख रहे हो? 3 ये और थोड़ी दूर तक फ्लैट जा रहा है, फ्लैट देन राइजेस. तो जैसे जैसे सेंट्रीफ्यूगल इफेक्ट क्लियरली दिख रहा है इसमें, इन सब में you can see that. So as I told you, for non-zero values of L, there will be centrifugal effect, which you will see. So these were the points, important points to note from these diagrams, from this graph. So what did you note? This point is L is equal to 0, amplitude is maximum at the nucleus, square of this gives you electron density. So of course you can say with confidence that you have maximum electron density for S, for any wave function having this, which is S orbital. S orbital के लिए ही wave function है वो. और हाँ, okay, so for non-zero values, when L is not equal to 0, so all these three, electron wave has zero amplitude at the nucleus. We saw that. Square of the term gives electron density, so electron density is 0 for all these functions, wave functions. As L increases, as angular momentum increases, electron density near the nucleus also decreases. Electron density near the nucleus. Now, words का थोड़ा सा shades different है. At the nucleus, near the nucleus, बहुत सटीक तरीके से आपको दिखे. Whenever you are writing, these are the things that when you write your descriptive answers, these words do matter. Whether you are saying at the nucleus, near the nucleus, what you are actually want to say. For s orbitals, I was saying that it has maximum electron density at the nucleus. For all these things, for others, it has 0 at the nucleus. Near the nucleus, electron density starts rising. It becomes non-zero. Lekin the rise is slower as the L value increases. 2, 1, 2, 3. The rise is slower. Electron density जो बढ़ेगा वो धीरे 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 rise होगा. और angular momentum, so the angular momentum increases. Electron density near the nucleus also. So electron density can be calculated from C. यहाँ पे electron density ज़्यादा है. अगर आप इस point पे लें, near the nucleus. This is the point near the nucleus. L is equal to 1 has higher electron density. L is equal to 2 is less, much less. L is equal to 3 तो almost 0 ही है. ठीक है ना? तो इस तरह से आपको, that is the point that is conveyed here. The electron density near the nucleus also decreases as L increases 1, 2, 3 gradually. क्या कोई लिफ्ट में फंस गया? लिफ्ट में. So then when L is not equal to 0, ये सिंपल मैथमेटिक्स है, ज़्यादा मुश्किल नहीं होना चाहिए. R is equal to, ये पॉइंट भी मैंने कहा था एक्सप्रेस में. अच्छा, can we rub it out? Duster. Okay. Thank you. ठीक है, ये पॉइंट तो देख लेना. R to the power L. So when L is at the nucleus, which means we are talking about R is equal to 0. R to the power L will be equal to 0. मतलब 0 का पावर 1, 0 का पावर 2, 0, 1, 2, 3 जो अभी हमने देखा, समझ रहे हो? लेकिन but when L is 0, then 0 R to the power L will be this. 0 का power 0, this is 1. For all other cases it will be 0. ये point बस वो line में कहा गया है. And that is pretty simple. So 0 radial electron density at the nucleus, zero probability of finding electron for anything which is having L non-zero. Higher orbital angular momentum, less likely to be found near the nucleus. We have seen in the previous slide. So higher, when L is zero, there is non-zero probability, then probability density of finding the electron at the nucleus. So there is exponential decay is an essential feature of this radial wave function. Exponential decay, e to the power something r के terms में आएगा. And it is because, as I told you in last class also, and it is because of this reason that we represent the orbitals as a spheres, electron clouds as spheres, because वो radially because of it is radially as you move away from the nucleus, on all sides there is decay of the amplitude, and so it will, if you connect those points of equal electron density, it will generate a sphere. Okay, so we will see some salient features and how it. So here, okay, so here the energy you will find from this equation, the energy can be calculated to be this z square mu e to the power 4 h cross n square. So this is a new quantum number that comes into picture in radial wave function. N for one electron system, it is the n which determines the energy. जब तक एक इलेक्ट्रॉन है, एनर्जी के लिए only this n is sufficient to describe the energy of the electron. But as soon as multi-electronic system हो जाता है, then a smaller contribution L also contributes to energy. ठीक है, that's why. So in general we can say, if we are discussing all the atoms, N contributes to the major part. For hydrogen, it contributes 100% to the energy. So when you're talking about quantum numbers, so radial wave functions depends on the values of both n and L, but not on ml, with L restricted to values that we already know, 0, 1, and -1. And so the radial wave function will have a form. So with 1 r to the power L term, then there will be a polynomial in R, and then exponential decay. So the three terms have three different roles. Decaying exponential in R, that is, you have to, the amplitude of the wave must go to 0 at infinite distance. So that part is here. Now in between the nucleus and the infinity, there will be oscillation of the wave. There must be curvature. That part will be defined by some polynomials. And r to the power L, that is to take into factor the centrifugal effect that we talked about. So even in a simpler terms, we define a quantity rho, which is which takes into factor zr by na naught. 2 zr by na naught is defined A, and a naught is the Bohr radius, which can be defined 4 pi epsilon naught h cross square, mass of electron into E. So here note that we are replacing mu with me, because reduced mass is very similar to mass of electron. So we can, for simplicity, for the sake of simplicity, we can write, we can replace mu with me. Okay, so this is what we find me. Sorry. So this me is actually, this is mu which has been replaced with that thing. So Bohr radius has a value of this was the same thing that was calculated by Bohr, 52.9 the radius. It's the same as appeared in that model, Bohr's model. So radial wave functions for electron with quantum number n and L are the functions. Basically you will have normalization constant and then the r to the power L term. So that was so that we talked about the r to the power L, and this is now accommodated in the rho, that 2zr by na naught, and this is Laguerre polynomial that takes into account for the oscillating nature. So this particular thing is that Laguerre polynomial. So polynomials have simple forms for rho 2 minus rho. Just see something we can. So this is the points, three different terms that we get separated: r to the power L, then polynomial. So three things we have written, and we are analyzing the role of each one of them. So the wave function radial part only, if you write, then it has one r to the power L term, then polynomial, and then exponential. So these are three terms that we were talking about. Exponential term ensures it is a negative sign, and it shows that it will continuously decrease and become zero at a distance far away from the nucleus. This r to the power L, this is the same thing that we are talking about. Don't get confused. This is same as r to the power L. R to the power L term, if L is non-zero, wave function goes to zero at the nucleus. So r to the power L ये काम कर रहा है आपका, जो सेंट्रीफ्यूगल इफेक्ट और वो सब जो हमने बातें पहले की थी, उस चीज को इसमें समा दे रहा है. इट इज जस्ट गेटिंग everything into that part is contained within this r to the power L term, that it will the wave function becomes zero. Wave function goes to zero at the nucleus. At the nucleus it will become zero. So वो r to the power L कर रहा है वो काम. जब भी L is whenever L is non-zero, the wave function will be zero at the nucleus. ठीक, तो उसके लिए ये वाला टर्म लाया गया है. एंड द थर्ड बीच वाला जो टर्म है लेग्यूरे पॉलिनोमियल, इन दोनों चीजों को कनेक्ट कर रहा है. देखिए दो चीजें, इंफिनिटी पे जीरो, न्यूक्लियस पे जीरो, ठीक है, एक्सेप्ट फॉर एल इज इक्वल टू जीरो टर्म. बाकी जितने भी वेव फंक्शन बनेंगे सब में यू हैव टू मेक द वेव फंक्शन जीरो एट द न्यूक्लियस. सो वन जीरो इज एट द न्यूक्लियस, देन अनदर जीरो एट द इंफिनिटी. तो वो उन दोनों का ख्याल रखा जा रहा है, इन दोनों फंक्शन. बीच में अगर वहां पे जीरो हो गया, न्यूक्लियस पे भी जीरो हो गया, तो वेव तो पूरा फ्लैट, मतलब वेव के लिए तो कहीं तक कर्वेचर होगा, कुछ तो एम्पलीट्यूड वेरिएशन रहना चाहिए. वो फंक्शन कहाँ गया? वो काम हमारा ये पॉलिनोमियल करेगा. दैट जॉब इज बीइंग डन बाय दिस Laguerre polynomial that shows the oscillatory nature of the wave. The basic thing that we talk about wave, we think of oscillations. So that oscillations is contained within this polynomial. Positive to negative, मतलब वो सब change होगा. And then if if, you can talk of modes also in that context. So तीनों का तीन different role है, well defined, three different types of. So we can see some of those functions in the next slide. I think we have the form of that. Okay, yeah, this point also like to clarify. जीरो जहाँ पे आ रहा है वो नोड नहीं कहलाता, सिर्फ जीरो होना नोड नहीं है। जीरो से मतलब प्लस माइनस और बीच में जीरो जहाँ पे होगा वही नोड पॉइंट। whenever you have something zero at the end, at the nucleus, zero at the infinity, those points will not be called node. Node is a point where you have a changeover from a positive to negative or negative to positive, and in doing so it goes through zero. तो वो जो पॉइंट हुआ जीरो वाला पॉइंट, दैट जीरो पॉइंट इज कॉल्ड नोड। ओके, so never, we should never get confused about why we are not calling that as node. ठीक है। So what is an orbital? When we talk of these things, simplest, one electron wave function is an orbital. ठीक है, अब वो सब भूल जाइए, वो जो क्या 90% प्रोबेबिलिटी ये वो कुछ नहीं, सिंपल, one electron wave function is an orbital. You can't think of an orbital. Orbital कोई, मैंने कहा ना, कोई कटोरा नहीं, कोई बर्तन नहीं है जिसमें इलेक्ट्रॉन आके रहेगा। ऑर्बिटल ऐसा कुछ होता ही नहीं है। ठीक है, अभी आप देखेंगे जैसे जैसे हम 3 डायमेंशनल उसका ग्राफ जो बनेगा वही डम्बल हो जाएगा, वही स्फेरिकल रहेगा, वो सब हो रहा। ऑलरेडी आपने देखा होगा हिंट जो अभी तक हमारे पास। सो so either way you can talk about orbital. This is the most modern way of saying what an orbital is. वो सब पुरानी चीजें भूल जाओ जो पहले तुमने पढ़ा होगा। Okay, so wave function, so when you, so this is how we say when you have n is equal to 1, l is equal to 0, and you have l is 0, ml 0, this is called 1s orbital. And an electron that is described by, so an electron wave that is described by these three quantum numbers will, can, is also said that it is also said that the electron is in 1s orbital, or the electron has 1s orbital state. So this is how we say said to be in the 1s orbital. बहुत finer things है, how you can refine your language when you are writing something, you are describing someone, what you mean by एक एक चीज जो word by word है बहुत अच्छे से यहाँ पे। So this is इलेक्ट्रॉन का वेव है, वेव, उस वेव को डिस्क्राइब करने के लिए ये L0 ML0 ये जो स्टेट है, दिस इज 1s ऑर्बिटल, एंड द इलेक्ट्रॉन जो वेव, और यू कैन, इन अनदर वे यू कैन से दैट electron wave that is described by this function, we also say that electron is in 1s orbital, or electron has a 1s orbital state. Okay, so we'll see more about this, how this restrictions on NL, sorry, the restriction that comes from this NL and ML, these quantum numbers. So why there is single 1s, or why there is 2p orbitals, 5 3d orbitals, so all these things. So simple, we are going to have a view of first few simplest radial wave functions. So simplest one, when n is equal to 1, n 1, l 0, we start with this. So the form of equation that you can see here is z by a. So that is a constant. If we are talking about hydrogen, z is constant. अगर हम सिर्फ हाइड्रोजन की बात कर रहे हैं तो z तो constant है, वो भी वेरिएबल नहीं है। z by a is a constant, and e to the power minus rho by 2. So 2zr by na naught. What we had written earlier, that was your so this is a simple exponential decay. Rho is equal to na naught. So this you can think of a constant term. So the function is a constant term e to the power minus a constant term and then decay minus 2zr by na naught. So as a function of n is 1, so a naught, simple a naught. Z, so 2z by a naught r, इस तरह से वेरिएशन आ रहा है. So similarly you can see here, so second again you have this kind of thing. So one more view, different kind of view. This is better. If we write, we can also the same thing can be also written in this form. This is, I think this is better way. ये ज़्यादा better है. आप इसमें ध्यान से देखिए. So this expression, so everything, all the things here are constant. This term is constant and this is exponential decay. So when you plot it, if you try to plot it, so constant times the exponential, when you plot this function r versus small r, then it will appear like, suppose, yeah, it will be going like this. So just an exponential decay profile. सिंपल यही चीज़ हम आज तक आपको हाइड्रोजन का जब बॉन्डिंग भी दिखा रहे थे ना, याद होगा, जब एक बार सर्कल बना के आपको एंगुलर पार्ट किया जो स्फीयर लाइक हुआ, दूसरा पार्ट ये था, ठीक है. तो सिंपल एक्सपोनेंशियल डिके, ये 1s ऑर्बिटल का रेडियल पार्ट आपका था व्हेन L इज n is equal to 1 and L is 0. This is your n, this is L. n और L का वैल्यू है, हाँ, n and L. So when n is, so this is the bit of, so in a similar way you can have second equation. So there is no point where, so you do not have a node. In first case there is no node, but in the second function you will have a node where the point where zr by 2a naught will equal to v1, or where r is 2a naught so this is the point where node at this point, at this value of r distance. So this is how you can, if equation is given to you, you should be able to find the distance where node will occur. node कहाँ पे आएगा वो आप इजीली निकाल सकते हैं. अगर इस तरह का चीज़ें आप देखें, जो एक्सपोनेंशियल टर्म है उससे नोड नहीं आता है, वो सिर्फ एक्सपोनेंशियल डिके दिखाएगा, ठीक है. इट इज ट्राइंग So if you are looking for nodes, how many nodes to appear, or so that point will be, you will get it from, okay, where is this? So the point of node, yeah. Okay, so let's clean up the slate. So इस तरह से if you go on substituting the values, so this was 1s, 2s, 2p, this is 2p orbital, and for this, so you can also see that 1s, 2s do not, so the electron density is not 0, the amplitude of the wave is not 0 at the when r is equal to 0, but for this one, when r is equal to 0, r21 is 0, the whole function goes to 0, है ना? So there is, so the amplitude of the wave is 0 for this point, and then it rises, ये सब देख रहे हो ना? So इस तरह से धीरे धीरे थोड़ा सा और टर्म बढ़ेगा, so you will have a large number, one, so there was no node in case of r21, now you have a node appearing in this 3s, 3p, 3d. So इस तरह से इक्वेशंस आएंगे. Now we can further write it in a different way and make it much simpler for you. और थोड़ा visualization को simple करते हैं, थोड़ा सा और. One more. So this is the equation that we were writing for 1s orbital. Okay. So all this term is constant. We can represent it through a constant k 1s. इसको हमने constant. This is a constant term. So this is a constant that we are writing here. Okay, k1s, and so a constant term e to the power minus zr by a naught. This is our equation for most simplified equation for the radial wave function for 1s orbital. इस तरह से हम लिख सकते हैं कि ये कांस्टेंट टर्म होगा कुछ, और उसके बाद एक्सपोनेंशियल माइनस zr by a naught. Similarly, if you analyze the second one for hydrogen atom, z is constant, and so you can treat everything outside this bracket. This whole thing is now constant as k for the second 2s orbital. So you can find out 2a by 2a naught by z is the as the term. Similarly, you can write this as third for the k2p, again all of these terms taken together in k2p, and including the r and a naught. This ये भी ले लिया गया है, including this z, including this r, सारा कुछ इसमें चला गया. सिर्फ r के टर्म को छोड़ के even a naught, this z and this whole thing is going into, ये सारा चीज उस कांस्टेंट में चला गया, सिर्फ r का टर्म बचा हुआ है उसमें. Okay, and so you can see the so what do you see here? पहले वाले केस में when n is equal to 1, the decay happens zr by a naught. For all the two cases, one thing is common, the exponential decay term is minus zr by 2a naught. ये जो 1s, 2s and 2p, ये आप देख रहे हैं ना. So the जब n इंक्रीज कर रहा है, जो डिके का जो प्रोफाइल है वो और स्लो हो जा रहा है. ZR, this ZR by A naught divided by 2, ZR by A naught है for 1s and for 2s and 2p. मैं ये कहना चाह रहा हूँ 2s 2p इनके लिए जो हाफ ऑफ ZR by A naught, ZR by A naught का हाफ जो उसके लिए डिके टर्म था माइनस दिस, तो वो टर्म हाफ हो गया है. मतलब जो पहले फास्ट डिके अगर हो रहा था, शार्प डिके, now it will be slower for longer far away from the nucleus. It will have likely to have finite amplitude of the wave. When the decay is faster, जैसे कि पहले के स्थान, मुझे लगा कोई है, you were looking somewhere there. So पहला जो टर्म था ZR by A naught था माइनस साइन के साथ, ठीक है. तो so there was, so the decay that was happening there in case of ZR by A naught, and this is half of that term. ये जो टर्म है डिके टर्म उसका हाफ है ये. मतलब पहले जितना डिके कर रहा था, रेट ऑफ डिके था विथ रिस्पेक्ट टू डिस्टेंस, चेंज इन आर एंड द एम्पलीट्यूड डिकेज, एम्पलीट्यूड डिक्रीजेस, दैट वाज हैपनिंग एट अ सर्टेन rate. Now that is much slower, that has become half of that. So this gives you a reason that you can draw 1s or 2s orbital will be drawn with a larger circle or as shown up to a larger distance. यही आपका reasoning है. Why you draw 2s larger than 1s? Because of this. 1s छोटा बनाते हैं, 2s को बड़ा दिखाते हैं, 3s को और बड़ा दिखाते हैं. क्यों? As you are moving from one, mathematically the decay has become slower, so for longer distance the amplitude remains finite, has a finite value very far away from the nucleus. जो पहले खत्म हो जा रहा था छोटा सर्कल था, अब उसका बड़ा करके आप दिखा रहे हो कि ये यहाँ तक इसका फाइनाइट रहेगा. मतलब इलेक्ट्रॉन डेंसिटी भी बहुत सिग्निफिकेंट रहेगी काफ़ी दूर तक. सो इसलिए आप इसको दिखा रहे. सो दैट इज वन ऑफ द रीजंस व्हाई वी mathematically I am showing you why it happens. Okay, so that is a simple to the scale drawing of a graph, to the scale graph. So this is the first function, radial wave function for 1s orbital. So this is how you can see it varies. Maximum value here, and then this is what we call as exponential decay, simple exponential decay that you get here. Then look at the second term, the profiles. This is what you get to see. So here there is a point, I told you there will be a node, और उस नोड के बाद वो नेगेटिव होगा और फिर एम्पलीट्यूड काफ़ी दूर जाके डिके करेगा. तो अप्रोचिंग ज़ीरो, so again it rises to a negative side, it rises and then goes to 0 on this side. So overall decay has to be slower. So you when you're touching this 0 part, finally it has to be at a longer distance. So ये 3 तक दिखा रहे थे यहाँ पे, जो मैंने कहा decay is slower. Now almost you are going to 5 times greater distance than touching over 0, this point. And so this is 2s orbital, this was 1s, this is 2s, and similarly if you try to see this slide, 3s again. So there will be 2 nodes, you can see one here turns negative, then again turns positive, and then decays to 0 at very approaches 0 at a large distance from the nucleus. ठीक है, 3a0 हो गया। सो डीके अब आपका और स्लो हो गया। देखिए जो एम्पलीट्यूड 0 तक पहुंच जा रहा है, काफ़ी और डिस्टेंस पे जाके 0 हो रहा है। सो दैट इज़ व्हाट आई मीन व्हेन आई से दैट द डीके इज बिकमिंग स्लोअर एज n इंक्रीजेस, n आपका बढ़ेगा, वैसे डीके आपका स्लो होता जाएगा। 1/3 ऑफ द फर्स्ट 1s का जितना डीके था उसका हाफ हुआ था 2s में, 3s में उसका 1/3 हो गया डीके टर्म जो यहाँ पे आप देख रहे थे। ठीक है, so we have discussed 1s, 2s and 3s. What did you observe? क्या क्या ऑब्जर्वेशन है आपका मेन? You have in all of them maximum electron amplitude of the wave is at the nucleus, whether it is 1s, whether it is 2s और 3s, सब में मैक्सिमम यहीं पे आएगा। ठीक है, नंबर ऑफ नोड्स ऑफ कोर्स इट is changing 3. You can also see a generalization that emerges is that number of nodes, how many nodes something can have. n minus l minus 1 एक जनरलाइजेशन आपको ट्रेंड देख के समझ में आ जाएगा कि ऐसा फॉलो हो रहा है। कितना नोड्स होगा फंक्शन में वो आप बता सकते हैं। सो एस ऑर्बिटल्स का हमने देखा, मैक्सिमम एट द मैक्सिमम एम्पलीट्यूड एट द न्यूक्लियस, square the term you will get electron density, that is also maximum at the nucleus, r is equal to 0. Now looking at the next functions, 2p orbital. So this is your plot of 2p. So at the nucleus it is having 0 at the nucleus, 0 amplitude, and then it zoom सीधा, जैसे ही 0 से आप थोड़ा सा नॉन जीरो रेडियस पे आते हैं, then it zooms up, it goes up and then reaches a maximum. Maxima is here, this is the maximum amplitude, the point of maximum amplitude है ना, and then exponential decay followed by exponential decay. So max rises to a maximum and then decays to 0 at the infinity, approaches 0, have typical exponential decay profile that is obtained. ठीक है, radial wave function. So this is 2p and this is 3p. अब 3p में क्या है, एक नोड आ गया, there is no node here, so you can again think of n minus l minus 1. कोई भी नोड नहीं है इसमें, 2p में नोड नहीं है, रेडियल नोड नहीं है, 3p में एक नोड आएगा. So the one node that appears is given by this. So this particular point is here. When you equate 6a0 is equal to zr, you get the value of r, the point where amplitude is 0. वो point यहाँ पे दिखाया है. ठीक है, similarly you can have this radial wave function. This is, ये किसका प्रोफाइल है, 3 2, मतलब 3D. This is the profile of 3D orbital, 3D. n is equal to 3, l is equal to 2, number of node is 0, n minus l minus 1 अभी भी आपका वैलिड है, सब everything is, so you are getting that. So so this is what we had just trying to tell you more about this. So we have changed the coordinates, we got 3 functions, r, capital theta, capital phi, 3 wave, the original wave function splits into r theta phi, and then we take these together. So take them together. This is your angular part, and this is called angular wave functions. So radial part and angular part we take together. So angular part is taken together, the theta and wave function. ये सब जरूरी भी था because otherwise the problem was that wave function जो simultaneous x y z का function था, एम्पलीट्यूड तो उसको आप ग्राफ कैसे प्लॉट करते? यू शुड इट वाज नॉट पॉसिबल टू एम्पलीट्यूड एंड देन एक्स वाई जेड, सो यू नीडेड अ 4 डायमेंशनल ग्राफ. जब आपने आर थीटा फाई में कन्वर्ट किया, so it was you were never you could have never drawn a 4 dimensional graph to understand the electron as waves inside the atom unless we did this चेंज ऑफ कोऑर्डिनेट्स. सो चेंज ऑफ कोऑर्डिनेट्स का बहुत ही बड़ा रोल है कि एक समझने वाले लेवल तक उसको ले आया, सिंप्लीफाई कर दिया चीज़ों को. नाउ यू कैन प्लॉट, इट हैज़ बीन, once you change the coordinates to r theta and phi from x y z, the things become simpler because now that it has 3 parts. So 3 wave function, it can be represented as a multiplication of 3 wave function, each of them depending on only one variable. So capital R depends only on small r, that is the radius. Capital theta depends only on theta, which is capital theta is the wave function that depends only on theta. Theta is the angle with the z axis. Phi is the angle with x axis. ठीक है ना? In the xy plane, x axis with the in the xy plane. ये भी मेंशन करना जरूरी है, नहीं तो x का एंगल इधर भी हो सकता है. ठीक है ना? एक्स एक्सिस इन दी एक्स वाई प्लेन, तो वो फाई है. तो ये तीनों को मल्टीप्लाई करके ये आपको सिंपल आर थीटा फाई, ठीक है, ये आपको आ रहा था. सो दैट इज, सो दिस angular part is taken together and we call it angular wave function. Radial part is taken together, that we have just discussed, radial wave function. So radial part depends on n and l, we have seen that. So it is crucial in determining the energy, probability of finding an electron at a given distance from the nucleus. The angular part will depend on L and ml, the quantum numbers. So as I told you earlier, square of the radial part, what does it gives you? Radial electron density, or we say radial density function. So this is probability of finding at a specific point. At a specific point, if you want to find the probability for the electron, that is given by this thing. Radial probability function, बहुत ध्यान दीजिएगा यहाँ पे. I need your attention here. Now we are at a very crucial point. और यहीं पे आपको जेडी ली और शिवर एटकिंस में डिफरेंस या हुई में क्या डिफरेंस है वो भी पता चल जाएगा. Square of the function, radial part of the wave function, radial density function. Radial probability function जिसको आप जनरली, जो आपको 12th में बताया जाता है, प्रोबेबिलिटी जो वर्ड आप सुनते थे, जो आपके कानों में जाता था, वो यही था, रेडियल प्रोबेबिलिटी फंक्शन था, जो कि it was a probability of finding the electron in a small volume, in a thin shell, spherical volume around the nucleus. That is different from that one. So ये दो points अलग, क्योंकि this is the multiplication of electron density into इलेक्ट्रॉन डेंसिटी वॉल्यूम, ये मल्टीप्लाई करके रेडियल प्रोबेबिलिटी फंक्शन आता था. ठीक है ना? सो इस तरह से विजुअलाइज करना है. At a distance r, you can imagine a thin shell of thickness dr, infinitesimally thin shell, and we are trying to locate the probability of finding the electron in this thin shell. ठीक है. And this thin shell, if you integrate it from 0 to infinity, it will make a sphere. ठीक है. So this electron density into volume, ये रेडियल, ये प्रोबेबिलिटी होता है. जो जनरल प्रोबेबिलिटी का ग्राफ आपको जेडीली में दिया हुआ है वो यही है, जिसमें एस ऑर्बिटल के लिए आपको 0 दिखेगा. आप आर्ग्यू करते ना उस समय कि सर उसमें तो 0 दिया हुआ है, आप कैसे कह रहे हैं कि यहाँ पे मैक्सिमम होगा. तो वो क्योंकि दे हैव मिस्ड वन स्टेप. If you plot, go step by step, capital R, the wave function, square of the wave function multiplied by the volume of the thin shell, then you will get the 1, 2, 3 maximum amplitude. So now we can analyze this better. So this part, if you are reading chemistry and you are trying to going through this inorganic chemistry books, you will find that this distinction is clearly made out in case of Shriver-Atkins, clearly made out in case of James E. Huey, but not in case of J.D. Lee. It straight away jumps from the wave function to the radial probability function without going into the radial density. So that confusion will remain. Somebody who is reading only J.D. Lee, he will never come to know about this part, that S में maximum electron density कैसे आया. So this dV, this small volume, it is easy to find out. 4 pi r square into dr, that is simple. If you thin shell का जो volume होगा 4 pi r square dr होगा. So square of the wave function capital R square, and then multiplication by the volume of the thin shell gives you the radial probability, which is this. Okay, sorry. So now you can see this thing. ये जो ग्राफ है ये क्या है? So capital R square, we have just seen that it is an exponential decay for 1s. Simple 1s के लिए अगर हम देखें तो simple exponential decay है. So that is the blue line that you see. The blue line that you see is the plot of R, capital R square, that is the wave function, square of the wave function versus this. The second term 4 pi r square dr, this volume, it is a quadratic function that is shown here. So ये जब when small r is 0, you are at the nucleus, the 4 pi r square term is 0. So overall so that's how you see this is rising like this. Okay. The multiplication of these two, graphically the multiplication of the two terms, ये दो ग्राफ हो गया, individually आपने 4 pi r square इसको प्लॉट किया. The multiplication of the two term is shown by the red line. Multiply किया तो initially देखिए at the nucleus situation क्या है? The electron density is maximum, but the volume of the thin shell is 0. So multiplication of the two term is 0. So the radial probability function for s orbital is 0 at the nucleus. As you now अब infinity पे चले जाइए, दूसरे छोर पे चले जाइए, तो एक छोर और दूसरा छोर infinity पे चले जाइए. At infinity, the value of 4 pi r square is very high. 4 pi r square is very large at the infinity, but the wave function has decayed to almost 0. So again the multiplication of the two term will be 0. But somewhere in between, इन दोनों के बीच में कहीं पे एक जगह ऐसा आएगा where both will have finite values and a maximum should be obtained. So that point is here. You are getting the maximum. So this particular point where you get the thin shell में जहाँ पे maximum, ये most probable radius कहलाता है. What is this? This is called most probable radius. We can not talk about the radius. We cannot be precise like Bohr, उतना की circle. So we say most probable radius, which has calculated in terms of calculation is same as the Bohr's value. So the maximum probability in the thin shell is at this point, at distance r. So ये चीज़ है जो जरूरी है समझना. So this is the point, situation at r is equal to 0, where 4 pi r square, this term is going to be, this term is 0 because r is 0. At large value of r, the capital R approaches 0 rapidly, and hence the multiplication term is 0 again, and somewhere in between. So these are two things that we analyzed, and third is the middle point where both are having finite value. ये जो point है यहाँ पे multiply करेंगे तो इससे higher value आएगा. So in between r and r both have finite values, so there is a maximum in the plot somewhere at this, and this is happening at r is equal to a naught, that is the Bohr's radius. For 1s orbital, this is for 1s orbital. Similar thing you can get for consideration will come for any other orbital. Okay, so जो आपको दिखाया जाता है जेडीली में, ये r का फंक्शन एक्सपोनेंशियल डिके, और उसके बाद सीधा ये वाला जो ऑरेंज कलर से जो है वो कि 0 एम्पलीट्यूड है, 0 प्रोबेबिलिटी है, सिर्फ प्रोबेबिलिटी वर्ड यूज है. अब प्रोबेबिलिटी मैंने दो तरह से कहा, प्रोबेबिलिटी एट अ स्पेसिफिक पॉइंट विच इज द सेम एज सेइंग इलेक्ट्रॉन डेंसिटी, एंड उस प्रोबेबिलिटी एट स्पेसिफिक पॉइंट में इलेक्ट्रॉन डेंसिटी इनटू वॉल्यूम थिन शेल, तब आपको थिन शेल में पूरा निकलता है वॉल्यूम ऑफ द थिन शेल. सो दैट इज वन गिवन ओवर हियर. तो ये अब हमें समझ में आया, कैपिटल R is the wave function, radial part of the wave function, squared it, you got it the electron density, multiply by 4 pi r square dr, you get the probability. So radial wave function describes the variation in amplitude of the wave as a function of radius. Radial density function describes the variation of electron density as a function of r, and it also tells you about the probability of finding at a specific point. And the third one is the radial probability function. It tells you the multiplication of the 4 pi r square dr in an incremental thin shell at a distance r with thickness dr, that is volume of the thin shell. Okay, okay. So okay, so beyond this point we will continue next class में करते हैं थोड़ा. yes.